Right guys, this is the start of chapter 18, which is about capacitance, storage of charge. So there's quite a lot of pictures in the PowerPoint to help you, but I'm just going to do a little bit on the contents themselves. So the only thing you need to know about the chapter already is the idea that capacitor is an electrical component. Here is its symbol, and that component of course must sit in a circuit, so charge, current and voltage. All of that's all that you need. Everything else in this idea of electrons moving around is the basic idea. Okay, most of this is mathematical and it's nice and straightforward mathematics, but we're going to introduce some kind of big ideas, and then we've got some other bits which are a little bit more interesting when we start looking at generic patterns of exponentials and things. Okay, so that's later in the chapter. To start with, what actually is a capacitor? Well, as the symbol hints at, it's actually a gap in a circuit. Okay, so we connect a voltage across this, and what it does is it moves charge from one side, from one of these plates where we have 3 electrons, and they're pumped off here, they're pumped through a battery, and they're pumped round to the other side. So it's a way of storing charge. What it does, and some symbols actually have the plus on one side, they're known as dielectric capacitors, certain type of capacitors, but if you connect them up, what you end up with is effectively negatives on one plate, positives on the other, and you end up with an electric field. And because that electric field, the positives being attracted by the negatives and vice versa, we end up with a really strong electric field in here that holds the charges in. So it's a way of storing up charge by using an electric field to hold it all together. Okay, so if we go back to the idea that we did with circuits, what they're actually doing is when you put that field together, then you are storing, because of the forces, you're storing energy. Okay, so effectively, while it stores up charge, it's a device used in circuits to take time, a certain amount of time, to store up a certain amount of energy. And that's kind of the big connections between the two parts. So it's kind of two roles, but they both kind of come together in that. Okay, so a little bit on this. A lot of it comes down to the fact of timing as well. So capacitors, because of this time it takes to put them around, which we'll do in more depth later in the chapter anyway, because it takes a certain time, we can use it as a timing device. So anything where time is important, computers, indicators on cars, stop clocks, or whatever it may be, they're all dependent on capacitors. Okay, resistors just slow down charge as they flow, charges as they flow around, these store them up. So they go hand in hand, they do a different job. Okay, now what happens is, if we go back to the idea, it takes this idea of storing energy because of a potential difference. Okay, it's going to store up potential energy. Then what happens is we get a very simple idea, and the more charge we can get in there, the more energy it stores. And what you'll find is it's a very linear relationship. Okay, Q is proportional to V. The voltage, the potential difference on your capacitor or across your capacitor from side to side, will depend on how much charge you got on there. If there's no charge, there's going to be no voltage. Okay, no potential. So in terms of linking that as a graph, V over Q is a constant. Okay, so we've basically got the idea that Q equals constant, and C or a K doesn't really matter, multiplied by voltage. Okay, and there is nothing about this that's complicated. It is literally down to whatever this is here. Okay, and how much voltage comes from the battery, but how much space you can fill charge in, or put charge and spread it out on, then what you'll get is things that match them together. Okay, putting K with a constant in there because we often use a K. So actual crucial equation Q equals CV. Fundamental equation. Okay, just as important as V equals IR, it's the equivalent of. That's to do with I, if you think about it. That's your V. Again, it's a multiplying constant instead of resistance, it's capacitance. Okay, symbols for it are those, but what they're measured in are farads. Now, farads are huge. If you took the whole Earth to be silicon, you'd find that actually you'd end up with about 4 or 5 farads for the whole of the charge that can be stored in the Earth. So it's a big value, okay? And the coulombs, again, that's a pretty big value as well. You know, if you have 1 coulomb of charge, that's a heck of a lot of current flowing around and being stored. Now, as I'll show you in the lesson, the actual ideas on how to get yourself a bigger value of, excuse me while I just adjust this. There we go. Bigger value of charge storage all depends on several things. One of which, the most obvious thing, is the physical size. So the physical dimensions. If you literally have, and I'll do a little bit of artistic license here, excuse me, if your capacitor from a three-dimensional point of view is basically a couple of parallel plates like that, parallel plates work best. Again, I'll demonstrate it in a video. Okay. That's literally edge on view is the symbol. Yeah, so if we have this this physical thing here, if we can actually make that bigger, physically bigger, then what we end up with is that we can actually get more charge stored on it. Okay. Now, actually, it's the charge that the area that overlaps. So if they don't overlap, the area where you can get your field storing up in the gap, yeah, is smaller. So yeah, it's actually the area, I'll put in brackets, of overlap, because that's where your field is. Okay, now we can change the gap as well. We'll come back to that one in a second. So the physical dimensions and size of the plate is what I'm after in the first one. We can basically have a stronger field. So let's just put it electric field strength. Which of course is the symbol E. Okay, from our old topic, we'll just be wary because we're going to talk about energy quite a lot. So that's the last time we'll use it in this topic, but it's to do with that strength. And that is dependent on the gap or the distance between those two plates. Okay, so that gap there. And then the last bit, well, if you want to get more charge, you could, rather like, for example, trains in Japan, if you want more people on the train, they employ people to shove you on. So basically we need something that is stronger at shoving charge on. So effectively it's the EMF or strength. Again, don't use that in the exam, but that IG is good. Strength of the cell. Pumping charges. Again, quite a visual picture, but moving the charges around the circuit. Okay, so pumping charges onto plate. Okay, so it's actually coming off one and onto the other one. It doesn't matter too much at the moment, but we'll talk about that in a later date. And so effectively, what we can do is, if I label in that little thing as a D there, we can sum this up nicely as an equation. So the amount of charge, excuse me, don't know what I'm writing there, the amount of charge depends on effectively the area times by the PD, okay, divided by the distance D. So I'm putting this in words, okay. It also depends on what you put in the gap. So the insulation, the area, and the PD. Now, insulation has a symbol, okay, which is epsilon. Okay, so epsilon, which we've seen before, to do with electric field strength, of course. So that is bigger. The bigger the insulation, the more insulating it is, the bigger that value, and therefore the more charge it can store. It has the area, it has the PD, and it has the distance between the plates. Okay, let's just put on area just to make it clear. Now if we compare that to up here, then what that shows is that capacitance is epsilon area over D. But if you think of it in terms of how much charge you can put onto the plate, it's much easier to think about how much total charge. But part of it's the capacitance, and part of it is how high you turn your voltage, how much you turn your power pack up. Okay, so nice simple idea, really, really useful, really common. So if we look at the designs, as we'll do later, the only way to change these is actually the physical sizes of it. Okay, and you'll see that a lot, or what we put in the gap. And I'll put that as a 0 at the moment, but it's very rare that we do air. Now, crucial bit is, of course, as you saw with our demonstrations for electric field, is that if we turn up the voltage between the gap too much, we get sparking. If you put the gap too small, we get sparking. Okay, so both of these together, both of these bottom two, give us something called the breakdown potential. Voltage, maximum voltage. When you buy a capacitor, it will have two things on it. It will have its value of capacitance, its ability to store charge, and it will also say what's the maximum voltage you can turn it up to. And again, different designs of capacitors designed differently with different gaps, different sizes and so on. So some tend to be really good at storing charge, but tend to only work for small voltages, or the other way around. Okay, so it varies a bit, but it all keeps coming back to this equation. So where does that equation come from? Well, we can do it by experiment, which is this thing down here that we'll pick up later. Or you can do it in terms of what we know already about electric fields. So we know, for example, that we can work out charge on a surface due to its electric field around it. If we take a circular one, then what we know is it acts as though the charge is at the center. So what I've got here is a circular, imagine a sphere. Okay, we have another sphere outside it, okay, but with a gap in the middle. And what we'll find is that because of the thing I mentioned with the last topic, Faraday's ice pail, you never get a charge inside. So if we charge up one of them, you'll find that the other one will end up cancelling it out. Okay, so that charge always equals out in a way. The one will be positive to cancel out, the other one must be negative. And because of that, we build up an electric field between them. So if we put a charge on the inside, okay, so here we'll put plus Q. What we'll find is, on this one, we'll get minus Q. Now, for those of us sharp-eyed, we'll realise that's at 0 volts. Does that matter? Yeah, it doesn't really matter, because what we're doing is moving charges in capacitors from one plate to the other. So we're going to take off Q's worth of charge from one of them, put them on the other one. Okay, the fact that we've taken it off there kind of gives us this, but relatively it just means that that is more negative than that. Okay, it doesn't actually mean that we need to have it negative. And because of that, we build up a nice uniform steady field. Badly drawn that one, because you know they're at 90 degrees to the surface. You get a nice steady field between them, not bad. And we also know, of course, electric fields have a direction, so they go from positive to negative. Yeah. So there is our kind of basic setup. We've magically managed to charge up the inside, and because of that we end up with a charge on the outside. Okay, so let's just put in produced here. Produced. So no net charge. That will not be needed for an exam, but you know, it's important to get the physics right, let's face it. So, sorry, I've done the old spelling in net as well, single T there. Now, because we know it's a radial field, well, we can work out its capacitance from our basic key equation, which is Q over V. But we happen to know V for radial fields, don't we? So let's put in that V equals 1 over, and you can beat me to this. Go on then, 4 pi epsilon. Okay, let's just call it epsilon in the broadest sense. Q, which we put on there, and the radius, which fairly obviously is however big this is. Okay, so that's our radius. That's generic, it works for both. But if we want the PD, that's delta V, that's going to be V2 minus V1. Okay, well, what we need is the voltage of one of them, we need the voltage of the other one, and we subtract them. Now, because they got some common factors, I'm going to just move some of that out. Okay, so that's going to equal 1 over 4 pi epsilon. Then we'll have Q1 over R, 2 over R2. Doesn't matter if it's the wrong way around, to be fair. Q1 over R1. Okay. Now these are, of course, the same Q because it has been formed by moving one round to the other. So we can simplify this even more. Okay, we haven't got a lot of space, so I'm going to just be a little bit sneaky here. So delta V equals Q over 4 pi epsilon. And then what we're going to do is, obviously that's going to be 1 over R2 minus 1 over R1. But I'm going to put them together. Okay, so 1 over R2 minus 1 over R1. Let's cross multiply that and get that cleaned out a little bit more. Okay, so that's going to be, let's check if I can remember my maths here. R1 minus R2 over R1 times by R2. And what effectively we've got there is that that's the difference in the radiuses, and that is 4 pi r squared. So if, let's clarify this out a little bit, if we can think of this in terms of the area, well, 4 pi is there and r squared there, think of that in terms of area, then actually that will work. But of course that's only going to work if those two are basically the same, because 4 pi r squared would assume the same r, but they're slightly different. However, and this is the big bit, if radii are large and similar, so not the same, but they're very similar, then R1 minus R2 is equal to the distance between them, and R1 R2 approximately equals R squared. Okay, so I'm going to sum it all up with capacitance Q over V. Oh, we've got our potential difference here, so let's make it delta V just to make it really clear. So the difference in voltage between the two plates, which is what that means in the first place. We've got V, so we need to flip it upside down. So what we're going to end up with is 4 pi epsilon r squared over, times by Q over Q, and that's going to be D. And the Q's will cancel out. 4 pi r squared is the surface area of a sphere. It is a sphere, so that basically means that capacitance equals epsilon area over distance. So mathematically we can show that this idea actually fits in with common sense, which is a logical way, a visual way of thinking, well, how much extra charge can I shove onto that plate. So use the logic, it explains the equation. It's much easier, I think, than the version we got here, okay, to work through, but it does mathematically make sense as well if you think about it. But again, we're doing a slight cheat by saying these are gigantic spheres with a very small gap between them. Okay, so this is definitely not to scale.
Right, before we look at different types of capacitors and how to test them, you might want to break and pause this here.
Okay, so what we've got so far is a hypothesis, mathematical. We've got a theory using common sense, but actually does all this work? Well, we need to actually check it. So classically, this is a big kind of area that the exam boards ask about because it's about your thinking. So what we're going to do is really link in some basic ideas from electric circuits to bring it all together. But this is a fairly standard example of a circuit involving capacitors. Now, if you've seen my demonstration already, the first one using the great big orange capacitor, the 100,000 microfarad, what we did was actually this. I just stuck a battery, if I cover that up, stuck a battery straight onto the capacitor and it filled up instantly. It didn't take a microsecond, well, maybe a few microseconds to charge it up. It was very rapid because the only thing limiting the charge flow was the resistance of the wire and the electric field building up in here. Okay, so we'll come back to that in more detail, but it does mean, as you saw, that when we basically switch it or connect some sort of resistor across the capacitor, then all the charge flows through. In our case it was a bulb, so the bulb glowed, but the glow was very large and bright to start with, and then it faded away, okay, when I wasn't adjusting it. So what this shows is you get a surge of current flowing out, and then the surge slows down and it gets smaller and smaller, the rate of flow. So it's not constant, but using a bit of cleverness, we can use this pretty standard circuit to charge up capacitor and then switch it across, discharge. So we charge, then discharge, charge, then discharge. And if we do it quickly enough, then we actually get quite a steady flow through this current. Okay, now it's a small flow, so we'd need something like a microammeter to measure it. Okay, so if we're flicking the switch over fast enough, then it's fairly steady. If we leave it, as you'll find out when we do the classic experiments, using the same circuit, as we discharge it through our loop here, through to switch B, and then through the resistor and back to C, it will vary. But as I say, if we click this over fast enough, then it can be done. Now in the lab, we normally use a little electromagnetic switch, a reed switch, to flick this back and forth. So we can adjust it, we can do experimentation, and we can find out how good different capacitors are. The thing that matters, again, linking from what we've had, it does matter on the size of the voltage, because obviously that gives you how hard the charges are pushed. Okay, that's your electromotive force. So if we put that voltage onto here, in other words, if we charge this up fully, then you will have as much voltage on the capacitor as you had on the cell to start with. Interestingly, it's the EMF, it's the full voltage, it's not the terminal voltage. We'll come back to why on another day. So what we do need is we will need to measure across the capacitor and check on that voltage, because we'll need that nice and steady. Okay, so that's our basic setup. We're measuring what's escaping, and we're going to measure how hard it's being pushed effectively. Now, of course, rate of flow of charge is that. So if we measure the current, we can actually get back to the charge. If we, and I'll just make out very clearly, if it oscillates frequently, then we can take that as a fairly standard, nice, steady flow per second. Now, what we'll do is effectively we're going to be charging and discharging, so effectively kind of end up with a sinusoid. Okay, so basically in terms of what's happening, we're charging the capacitor in that side of the loop and the next half cycle as well, and then here we've got our discharge side. Okay, so can we link frequency into this? The frequency will give us the time. Obviously that's our link. So if we think about the time period, okay, so there's our gap there, and just make it nice and clear. So that's for our time period of our switch. Well, that's going to be equal to two different processes, charging and then discharging. So we're going to use the idea of T. Okay, so T is this process in that section, okay, or that section, it doesn't matter. And of course T, time period is 1 over F, so we can do some maths to give us something logical. So T for our processes of our calculation is going to be 1 over 2F. So whatever frequency we have got on the switch, okay, so frequency of the switch. Just make that clear there. Okay, so that links it in. Now if we're using Q equals IT, then we can just simply put that in. Q, in terms of usefulness, I'll come back to in a second, this is obviously I over 2F, yeah, but Q on its own we don't really want. What we want to know is this experiment is to find out about the charge. So again, going back to the equation, the key equation for capacitors, then instead of Q we can write CV. Okay, so quite simply we can work out from, it doesn't really matter which way around it, we can work out various variables, we can experiment with various variables to get something useful. So if we are after, for example, changing, I don't know, the insulation in the middle, or the area of the plates, or the distance between the plates, all of those become variables in our equation. So the key with this is, as an experiment, of course, we need to think about the variables. The thing that is controlled by everything else will be your current. So your current is always going to be dependent on whatever you're changing. So down here as an experiment you could try F, but that doesn't affect the capacitor. The voltage doesn't affect the capacitor, but both of them do affect the current. Okay, so you'd have to control them and keep them the same, keep them constant. However, as an experiment you'd either be changing epsilon A or 1 over D. Okay, and if you did that you'd end up with a lovely nice straight line. Okay, and from that you can get your known values. Okay, so your gradient will give you your conclusion. So similar process to every practical, but yeah, this circuit you will see over and over in this chapter. It's a key kind of thing. 2-part cycle. You're charging it up, you're filling up your capacitor, and then you're emptying it. Okay, so have a think about that in terms of practical exam questions. You know, it's back to the same things. What will change? What's going to depend on what? What's my dependent variables? And then how am I going to do this? So for a range of areas, for a range of overlap of our plates, for, you know, whatever it may be, it could be distance between the plates. In terms of in the classroom, we tend to do the area because it's the easiest one to change and get a whole load of different readings. It's quite hard to do the distance, and it's definitely hard to change the insulator very consistently. Now, to get your head around the idea, we do have a section here. Okay, this will get you imagining and thinking, and if you play with PHET, you can start to see why things are happening. Okay, however, in the exam, this scores no marks, so that is very, very crucial because you cannot see it. Okay, you cannot see what's going on. The only way you can tell what's going on is by measuring potential differences in different places. Okay, but I think this is a really useful concept. Okay, and again, I'll put it there. If you haven't looked at it already, go and have a look at the capacitor lab on PHET and have a little play. All right. Now, to bring it kind of around full circle, there are different types of capacitors, and they all have slightly different uses depending what they are, what you want to do with them. Most of them of the Swiss roll variety, so you're getting a large area, so you can store a lot of charge. What we tend to use if we want a big capacitor is we'll actually use an electrolytic capacitor. Okay, now electrolytic capacitor, it's a bit hard to see on your diagram, probably easier in your notes, is that your salt in the middle, your brine, salty solution soaked into here containing electrolyte, when you put a voltage on it, you actually get a very thin layer deposited. You get a reaction, chemical reaction, you get a deposition on one plate, and it's that acts as the actual dielectric, okay, the insulator in the middle. The brine conducts, so actually the plate is brought right into the surface, so you've got a very thin layer. So the fact that it's a thin layer means that D is very small, so you get a really large capacitance. Okay, so this is really, really good for storing charge, but because it's a thin gap, you can get charges jumping across. So the voltage rating, shall we say, is rather low. The maximum voltage, the operating voltage, is low. Okay, so please notice that. However, because E equals V over D, so you've got a small d, great. Other useful ones you'll see, you will see these ceramic capacitors. They are literally layers of ceramic in between the two plates. It could be mica rock, so there's different types. This one tends to be where most mica is used. But yeah, you get very thin layers of insulation. They're really small capacitance, they're nano and picofarads. However, they're mainly to act as a gap in a circuit, so they're a way of stopping surges of current going through things. Okay, so very useful in high frequency circuits to stop, to buffer spikes of current, melting electrical circuits and things like that. Couple of adjustables, again using common sense, we can change the overlap of the area. So this is, you can spin these round and our plates will cross over more or less, and it's the area of the crossover that matters. Okay, so that would give a bigger capacitance than that because there's only my fingers at the moment crossing over. So you can adjust them, and the size of the overlap is where the electric field forms, and that's what stores the charge. So area on that one, very adjustable because it's quite easy to spin. However, you can tune circuits in with this kind, and what you use is a little screw on here, so it's pre-fixed in most places. You'll see this, and what they do is they screw the two plates closer together, so they squeeze the layer of mica, which is a very thin rock, very coarsey, shiny rock, often seen in the Alps. And when you squash it down, you squash the gap. Okay, so this one's adjusting D. Okay, so that's the one that matters, whereas over here it's the area that varies. Okay, so two types of fixed capacitor, adjustable capacitors. Two common types. There are others that tend to be cheaper and just used in different places. Some take high voltages. We're not going to worry about that. Now the bit that makes the most difference is, again, what the type of insulator is. So not just the fact it insulates and that it's physically thin, but actually changing its ability to store charge. So just like, again, the PHET animation with the balloon on the wall, what you can do is, if you have the right kind of dielectric in the middle, sticking an electric field on polarizes the atoms inside. And because of that, you're changing the gaps effectively between your positive and minus charges, your electric field section. Okay, so because of that, that again multiplies up the scale, and there'll be a relative permittivity that you multiply your absolute permittivity with. Okay, so in the data book you might see epsilon in equations, that's a generic one, but yeah, it's all relative to free space. So whatever your multiplying factor is, multiplied by the value in the front of your data book will give you the actual thing. Most questions tend to be with an air gap in. Okay, so again, back to there. Go and have a play with the lab if you haven't already. Now, just to finish this off, again, as we start moving towards circuits, trying to think about how they fit together, you want a really quite a nice simple understanding. So, the top of the sheet, I think this is a really nice little analogy. Okay, the devices to store charge, these are tanks of water, say, designed to store water. Okay, they can have the same volume, so they can have the same capacity, but what works different is how quickly charge flows in and out. So if you were to think about water tanks and you were to put a hole in the bottom, this one will flow out much quicker because it's much deeper. Okay, so this effectively, this depth is equivalent to the potential difference. So for the same amount of charge, you can either have a small capacity at a large volume, or you can have a large capacity at a small volume. Okay, but both of them will still fill the same amount of charge or hold the same amount of charge. Okay, so have a read through here. I think it's quite a nice little analogy, and that is a really big introduction, but really important. Get your head around it, get it clear in your head how you're thinking about what capacitors do. I've shown you some mathematics about it, but actually the crucial bit is using that basic equation of Q equals CV, you know, the Ohm's law equivalent for the capacitor world, using that and thinking about how you represent that in your head. Okay.